We are going to end the chapter talking about in detail a few more things with Earth and its atmosphere. So 5.3, as you can see in the title here, Earth is just right. So remember I kind of mentioned it earlier about Earth being in what we call the Goldilocks zone. So there's so many things that when we look at Earth, the water that we have here, what our atmosphere is like, how far we are away from the sun, all of those things really make it literally just right for life. And you can start to see the reason why we do call it being in the Goldilocks zone. So Earth's surface temperature stays within a nice narrow range. It's not too hot and it's not too cold. If you look at this table here on the side, look at Earth. Minus 88 degrees Celsius, upwards to 56 degrees Celsius. So we have a nice range. When you look at some of the other places, you can see the farther out you go in the solar system, Jupiter, Saturn, Uranus, and Neptune, really cold. You got to start to imagine just really how far away they are from the sun. And that's the reason why they're so cold. They're not getting as much energy as the inner planets, Mercury, Venus, Earth, and Mars. If you look at Mercury, look at the huge temperature swing there, anywhere from minus 170 to 390. So remember that water is going to freeze at 0 degrees Celsius and it's going to boil at 100 degrees Celsius. So it gives you just an idea of how big that actually is. Look at Venus. We talked about Venus before, having that really exaggerated greenhouse effect because all of the carbon dioxide in its atmosphere, look at that, 450 to 480 degrees Celsius. Just look at how warm it is there on Venus. So the average temperature on Earth's surface is about 15 degrees Celsius. And I know we're not that familiar with Celsius, but think about room temperature being at about 22, 23 degrees Celsius. So if you were to have a thermostat set at your house, most of us are familiar with that 68, 70 degrees Fahrenheit. You would have it set to around 23 degrees Celsius, 22 degrees Celsius, somewhere in there. So the average temperature on Earth is about 15 degrees Celsius when we look at an average. And as you can see on this picture here, if I look at the average land surface temperature, the blues are going to be cooler, and then the yellows are going to be on the right-hand side there. Yellow and oranges, they're going to be more warmer. You can start to see a pattern emerge. If I look near the equator, which is in the middle of the Earth, I can see it's consistently warmer compared to the places that are near the poles. And what does that have to do with? It's amount of sunlight. So near the equator, those locations receive a much more direct sunlight throughout the year than the places at the poles. And one of the videos you guys are going to watch this week, or if the video you already watched showed you that, where we use a flashlight and pointing it directly near the equator versus when we put it near the poles, it's going to be more spread out. So the sun's heat reaches Earth by a transfer of heat called radiation. So remember, just through the air, and it doesn't need particles to do that, which is a great thing because space is a vacuum. But it gets to us from the sun by the process of radiation. So through the air. Then we also have convection and conduction on Earth's surface. Remember, conduction is heat transfer by direct contact. So it can directly heat the air above Earth's surface. And then convection is when we have those currents forming, where you're going to have warm things rising and then cool things sinking. So once heat has arrived on Earth, there's those three ways that we can still have that light to be, or that heat to be continued to be transferred: radiation, convection, and conduction. But we get the sun's energy by radiation. So not all things heat up at the same rate. And we use the term specific heat to talk about that. So specific heat is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degrees Celsius. So how much energy do we need to put into something to get it to raise the temperature of it by 1 degree Celsius if we had a gram of it? And not all things would be equal in that sense. We talk about water and land a lot because we're in an earth science class. So compared to land, water has a high specific heat. So what does that mean? It means we need to put more energy into the water to get it to heat up than we would the land. I'll say that again because it's such a weird thing that we don't deal with normally. In order to heat up the water, we would have to put more energy into heating up the water than we would the sand. So kind of as silly as it sounds, if you wanted to heat up some sand on your stove and heat up water, you would actually have to put more energy into the water to get those molecules moving. So water actually hangs on to its temperature longer than land does. So even though these things that we just talked about seem like, oh, it's really confusing, we all know this living in northern Minnesota. We know that if I want to go swimming in a lake, I probably shouldn't go in late May, right? Maybe the later June, early July. Now the water's had enough time to get warmed up by the sun. So water takes a long time to heat up and it takes a long time to cool off. Whereas land is completely different. Land heats up quickly, it cools off quickly, so therefore it has a lower specific heat. So water has a high specific heat, land has a low specific heat. And we're going to get more into this later on, but that plays a big role in actually weather. And if you're in a location near a large body of water, that can greatly affect the weather in the area. Once again, we're close to Duluth, Minnesota. If you've ever watched the weather around here, you hear all the time, the lake effect, the lake effect. Lake Superior is one of the biggest bodies of water, on Earth. That lake greatly affects the weather around it. The water greatly does. Once again, go down to Canal Park. Even June time, you may have to have a coat on because Lake Superior is still really cool. And it's so big, it actually really never cools, warms up that much, but it does get a little bit warmer as the summer goes on there. So Earth's motion, the motion of Earth also helps to balance its surface temperature. So we have all of these things playing into balancing this temperature. We have our atmosphere, but we also have the fact that we are spinning really fast. So the Earth spins on an axis, and that spinning on its axis is called rotation. So the turning motion of a planet as it spins on its axis is its rotation. And on Earth, it takes 24 hours or 1 day for that to happen. So for Earth to make one spin, so if we're in math class, 360 degrees, or let's use you as an example, take wherever you are pointing right now in your room. Let's say you're standing towards your door, do one whole turn of your body and go back to the door. That would be one rotation. So on Earth, it is 24 hours to make one spin. And we're actually moving quite fast when you think about how large Earth is to make that spin. Revolution is the motion of a planet around its star. So it's kind of like a race car that's moving around and around a circular track. So just like this race car would be moving around the racetrack, Earth is moving around the sun. So we are in this revolution around the sun. It's also called orbit. And it takes Earth 365.25 days to make one trip around the sun. Now you notice I said a weird number there, 365.25 days. So we used to just do 365 days, and then we figured out we had some issues with the seasons. They weren't lining up anymore. So that's when they threw in the leap year. So that's a whole reason we have the leap year, is because a revolution around the sun actually takes 365.25 days to go around the sun. So by accounting for leap years, it helps keep things in check. They're about every 4 years, but it's not necessarily that. There's actually quite a complex mathematical formula that they use to figure out leap years. Now, when you look at the planets in the solar system, so think of the planets that are closer to the sun, they're on the inside of the racetrack, right? They're going to take a quicker amount of time to go around the sun. So Mercury, for example, the planet that is closest to the sun, only takes 88 days to make one trip around the sun. So think about that. If you lived on the planet Mercury, you would have a birthday every 88 days. Pretty cool, huh? You'd be a lot older than you are now. Whereas if we look at the planets that are in the outside of the solar system, so think of Jupiter, Saturn, Uranus, and Neptune, they take much longer to go around the sun. So some of the planets, Neptune and Pluto, in an average human lifetime, they're not even going to make one trip around the sun. So Earth's rotation and revolution takes it 365.25 days to make one trip around the sun. Now our orbit is almost circular around the sun. In astronomy, we actually use a term called an ellipse, which is kind of like an egg shaped, but for the most part, it really is quite circular as it goes around the sun. But just so you know, for scientific purposes, there is times when it's a little bit closer and it's a little bit farther away. So temperature and Earth's rotation. Even though Earth is farther away from the sun than Mercury, our night side never gets as cold as Mercury's night side. Why is that? Mercury doesn't have an atmosphere. And look at the length of the day on the planet Mercury. 58 Earth days. So I kind of used the analogy before. I don't know if you remember it. It's kind of like taking a burger and setting it on the grill and just walking away. It doesn't spin fast. So because it doesn't spin fast, you have this one side of the planet Mercury that is baking and cooking while the other side is quite cool. So think about the other thing too. I just mentioned that Mercury takes 88 days to go around the sun. So think about that. Technically on the planet Mercury, a year is longer than a day. Or shorter, yeah, I said that right, longer. Pretty cool. So Earth spinning fast on its axis helps maintain a constant temperature on the planet. I gotta go back to that. I feel like I gotta say that again. So yes, a year is longer, but look at that. A day is almost the length of time as a year is, which is just so weird. But just remember what that means when we say a day or a year. So a day is how fast it takes to make one rotation. A year is how long it takes to make one trip around the sun. So Earth spinning fast on its axis helps maintain a constant temperature on the planet. It's kind of like you've ever seen those rotisserie chickens cooking in the store. That spinning helps make sure everything stays the same temperature, the fast spin. So the difference between the day and night side of Mercury. So Mercury really hot on the daytime side because it takes so long to spin, whereas the nighttime side very, very cold. Finally, the last thing, I'm not going to go into too great a detail here. I think the video does a great job of it this week, is really why we have seasons on Earth. Now, I did mention earlier that sometimes Earth is closer, but it's not really that much closer. And here's the other ironic thing. We are actually, in December, like 21st, we're going to be closer to the sun than we are in July. So how does that work? We have seasons because Earth is tilted on its axis. So we have wonderful seasons here in northern Minnesota. A really distinct spring, summer, winter, and fall. For me, I think it makes life really exciting living here. It doesn't look the same year round. Even though we can kind of be grumpy about winter, we really get a nice change in seasons. And why is that? Because we are tilted. If the Earth was not tilted, you would have very consistent daylight. You would have very, very consistent temperatures. They would not change as much. So we are coming into winter here soon. So I'm going to start there on the left-hand side. So the first day of winter in the northern hemisphere is around December 21st. Now look at the axis. Look at the northern part of the globe there. We are pointed away. What's also happening around here? Are we getting less and less daylight? Oh my gosh. It gets dark late. You feel like, if we were in school, it's almost like there's no daylight. And you can see why. Look at the northern hemisphere. We are pointed away from the sun. So the first day of winter, which is usually around December 21st, look at us. We are pointed away from the sun. So not only are we receiving less direct sunlight, so it's going to make our temperatures lower. We are pointed away. So now as we move into spring, you can start to see, okay, getting more light. And now look at the first day of summer. So that's usually in June. So like June 21st there, first day of summer. Now we are pointed towards the sun. So we get more sunlight. Those days in the summertime when it's like bright early and then it's like the sun is out until 10 o'clock at night. Now you can see why, because we have more direct light. And then now you're going to see that pattern repeats all the way over again. You can start to see too, the more north you get, if it's the winter time and it's more north, there are some places that do not get any daylight at all in the winter time, or they're going to have 1 or 2 hours of daylight. Versus in the summertime, there's parts of Alaska where they receive almost sunlight the entire day. So think about that. They only have darkness for a couple hours of the day. So really kind of an interesting thing, but you can see that is what causes the seasons, is because we are tilted at 23.5 degrees. If we were not tilted and we were straight up and down, we would not have the seasons.